Hello everyone, hope you are doing good. Today we are discussing the theory part or the details on eigenvalues and eigenvectors from matrix algebra in engineering mathematics. So let's start with our topic. Eigenvalues and eigenvectors. Let A is equal to Aij be an n by n matrix. So consider a matrix of Aij, the order of the matrix is n. Then the matrix A minus lambda I is called characteristic matrix of A, where I is identity matrix. So there is a matrix A. We are taking the another matrix A minus lambda I, that is called the characteristic matrix of A, and the determinant of this particular matrix, that is determinant A minus lambda I, is called the characteristic polynomial of A. There is an equation, the determinant of A minus lambda I is equal to 0 is called characteristic equation of A, and its roots are called eigenvalues. So we are coming to what are called eigenvalues and eigenvectors. So first we'll discuss what is eigenvalues. We have an equation, the determinant of A minus lambda I is equal to 0. That particular equation is called characteristic equation of the matrix A, and from that particular equation we are getting the values of lambda, and the roots are called the eigenvalues. So the problem of finding the eigenvalues of a matrix is called eigenvalue problem. Simple. And if lambda is a characteristic root or eigenvalues of an n by n matrix A, then a non-zero vector x such that Ax is equal to lambda x is called the characteristic vector or the eigenvector of A corresponding to the characteristic root lambda. So if lambda is the characteristic root or the eigenvalues of the matrix A from the above equation, then a non-zero vector x such that Ax is equal to lambda x is called the characteristic vector, that is called the eigenvector or the characteristic vector of A corresponding to the characteristic root lambda. So these two equations you have to remember. So if determinant A minus lambda is equal to 0, then it's called a characteristic equation of the matrix A, and its roots are called the eigenvalues, and Ax is equal to lambda x, where x is a non-zero vector, is called the characteristic vector or eigenvalue of A, and it corresponds to the characteristic root lambda. Next we have some relationship between the eigenvalues and eigenvectors. So lambda is an eigenvalue of a matrix A if and only if there exists a non-zero vector x such that Ax is equal to lambda x. So suppose lambda is an eigenvalue of a matrix A, then the condition is Ax is equal to lambda x, where x is any non-zero vector. If x is a characteristic vector of a matrix A corresponding to the characteristic value lambda, then kx is also a characteristic vector of A corresponding to the same characteristic value lambda. Here k is any non-zero scalar. So if x is a characteristic vector, as we explained in our earlier statement, if x is a characteristic vector of a matrix A, then which corresponds to the characteristic value lambda, then k we are taking it as any non-zero scalar, then kx is also considered as a characteristic vector of A corresponding to the same characteristic value lambda. If x is an eigenvector of a matrix A, if x is an eigenvector of a matrix A, then x cannot correspond to more than one eigenvalue of A. So that is also an important thing. If we have x as an eigenvector of a matrix A, then x cannot correspond to more than one eigenvalue of A. So this x can be a value which is corresponding to one eigenvalue of A, not more than one eigenvalue of A. Suppose lambda is the eigenvalue of the matrix A, then x corresponds to the eigenvalue lambda only. There is no other value to which it will be corresponding. The eigenvectors corresponding to distinct characteristic roots of a matrix are linearly independent. So we will have multiple eigenvectors for a matrix and multiple roots or eigenvalues for a matrix. So the statement is the eigenvectors corresponding to distinct characteristic roots of a matrix are linearly independent. So 1 vectors will be corresponding to 1 roots of the matrix, characteristic roots of the matrix. So those will be linearly independent, won't be linearly dependent, it will be linearly independent. Next, we have some properties of the eigenvalues. Let's see them. Sum of all the eigenvalues of a matrix is equal to the sum of the elements of the principal diagonal. So we have a principal diagonal for the matrix. So we have the sum of the elements of that particular principal diagonal. So the sum of the eigenvalues of a matrix will be equal to the sum of the elements of the principal diagonal. Product of the eigenvalues of a matrix is equal to its determinant. We have eigenvalues of the matrix like lambda 1, lambda 2, lambda 3, etc. So the product of those, that is lambda 1 by lambda 2 by lambda 3 by etc., that will be equal to the determinant of the matrix. The product of the eigenvalues of a matrix is equal to its determinant. If lambda is an eigenvalue of a matrix A, then 1 by lambda is the eigenvalue of A inverse. Just remember this equation. Maybe in some numerical problems you have to apply these properties of eigenvalues so that you can easily get to the answer and you don't want to waste much time on that particular question. So just remember, if lambda is an eigenvalue of a matrix, it's an eigenvalue of a matrix A, then 1 by lambda is the eigenvalue of A inverse. If lambda is an eigenvalue of an orthogonal matrix, then 1 by lambda is also its eigenvalue. Suppose A is an orthogonal matrix and we have lambda as an eigenvalue of that orthogonal matrix A, then 1 by lambda is also an eigenvalue since it's orthogonal. If lambda 1, lambda 2, etc., lambda m are the eigenvalues of a matrix A, then A raised to n has the eigenvalues lambda 1 raised to n, lambda 2 raised to n, etc., lambda m raised to n. We have a matrix A and its eigenvalues are lambda 1, lambda 2, lambda 3, etc., lambda m. So then we are taking the matrix A raised to n and the eigenvalues of the matrix A raised to n will be lambda 1 raised to n, lambda 2 raised to n, etc., lambda m raised to n. So in this section we have a theorem with us. It's called Cayley-Hamilton theorem. So the theorem states every square matrix satisfies its characteristic equation. That is if for a square matrix A of order n, determinant A minus lambda I is equal to minus 1 raised to n lambda n raised to n plus A1 into lambda raised to n minus 1 plus A2 into lambda raised to n minus 2 plus etc. plus An. So every square matrix satisfies its characteristic equation. It has a characteristic equation which is A minus determinant A minus lambda I is equal to 0. Okay. So that every square matrix satisfies its characteristic equation, that is for a square matrix A of order n. We have this, then matrix equation x raised to n plus A1 x raised to n minus 1 plus A2 x raised to n minus 2 plus A3 x raised to n minus 3 plus etc. plus An into I is equal to 0 is satisfied by x equal to A. It's satisfied by what? X is equal to A. From the matrix equation it is satisfied by x is equal to A. That is A raised to n plus A1 into A raised to n minus 1 plus A2 into A raised to n minus 2 plus etc. plus An into I is equal to 0. So these are the basic properties and details from the topic eigenvalues and eigenvectors from the Matrix Algebra part in engineering mathematics. So it's a very simple topic, and in the upcoming videos I'm planning to put more and more problems from this topic, so it will be more easy for you to understand the details. So friends, please note down these points which we discussed today. This will be really helpful in direct as well as indirect questions. For the in the indirect questions, what you can do is you can just apply the theorem or the what you call properties of the eigenvalues and eigenvectors, and you can just find out the answer quickly. In 1 or 2 minutes you can quickly find out the answer without any delay. So thank you guys, thanks for listening. If you have not subscribed, please subscribe to my channel, and please give the suggestions for the upcoming videos. So thanks a lot.